The meeting is being recorded. And just a quick sort of recap, if you weren't there, Andrew's been with us for 7 months now. We've managed to extend him a little while, but that time is coming to an end. And obviously he's been working on looking at different options for using machine learning techniques to get more out of some of our data collection methods, particularly obviously continuous monitoring. That's kind of what we pointed him at. And yeah, so as that Alan Turing internship comes to an end, we're really keen to kind of get Andrew to kind of divulge what he's found to the group, and we'll record this so it can be available for others later on. So if that's okay, Andrew, I'll pass over to you.
Hi, thank you. But yeah, I'm Andrew. I'm usually a final year PhD student at the University of Leeds. I specialize in data science and sort of freshwater ecology. So seeing this internship come up was kind of a pleasant surprise, really. You don't really get a lot of data science projects in freshwater. So it's been quite a fun challenge looking at these sort of freshwater quality sensor networks. I don't really deal with water quality data very often. It's quite different in structure to the ecological data I'm used to working with, but it's been quite a fun challenge, really. So I sat down at the start of the project. We spoke with Matt Lowenthal, and I spoke with Simon Bichelle, Matt Fry, and various people about what we actually wanted to accomplish from this project. What sort of techniques did we want to develop? And the overall idea is that part of what Casca will be doing will be developing these sort of high quality, high density, different layered sets of data collection. And a big part of that will be a few of the demonstration catchments are going to be deploying these sort of high density sensor networks. They'll be collecting data in real time. And what we want to be able to do is make it so that you've not just got data coming in and being saved in a spreadsheet, but that there are these automated tools working on top of that to sort of help with some of the data processing, detecting these abnormal events, sort of flagging when sensors are malfunctioning and stuff like that. We want to be able to turn it from just raw data coming in into this sort of smart and reactive sensor network. So for my part in that, I have been looking at the techniques that could be used to help tidy the data, label the data and stuff like that. There's been particular focus too about, how do you get the most bang for your buck? Sort of how many variables do you need to be looking at per sensor, at each site to be able to distinguish between different types of abnormal data? How many sensors do you need overall in a catchment? And, just a rough estimation of what variables are actually giving these models the most information. So we had these three clear goals. We need to be able to detect abnormal data in a from each sensor. So this is working on the idea that the majority of the data coming in from a sensor should just be sort of normal baseline data. It doesn't rain most of the time. There's not a fertilizer being spread on a field most of the time. Most of the time, it should just be data driven by the large sort of diurnal and seasonal cycles we expect. Then we need to be able to classify that data into different types. And then we just, as a little bit of an extra, we're like, okay, well, if we've got a malfunctioning sensor, how well can we reconstruct the data from that sensor? So I've largely been looking at the Wensum DTC catchment for the project. For those who don't know, this was originally a DEFRA project between 2011 and 2014. It was an experimental subcatchment where they looked at sort of different sort of land use management strategies. As part of it, they deployed 7 high-quality multivariate SONs across the entire catchment. The data has actually, the sensors are still going and are still being maintained. So they now have 10 years worth of data that we managed to get access to for this project. I went through and sort of got out the labeled data, clustered it all together, and found, overall there were about between 2 to 9 different types of anomaly, types of different pollution event and sort of rainfall events and stuff like that. Sensor F here is the downstream sort of outsourced sensor. DC, M, A, B are all in the tributaries, and sensor E is kind of our midstream sensor. So then I started looking at building models in the Wenson catchment. Now, the initial idea was could a single model do all of stage 1 and 2, so be able to distinguish between normal and abnormal data, and then simultaneously classify the abnormal data into different types. So this would be what we would call a supervised classification model. You would train the model on all of the data that you're feeding into it, where you've got sort of each grouping of each different type of abnormal data and the normal data labeled. I looked at two different types of methodology here, two different types of model. I first looked at something called a recurrent neural network. This is a sort of a time series neural network that is able to sort of use the pattern of previous data, so the curve of the previous data, to help predict what the next data point should be. I kind of looked at these first because I had this idea that it's not just the values of each variable you're monitoring, such as conductivity or temperature at each timestamp that's important, but it's sort of that pattern of what has happened before that would help the model distinguish between these different types of data. And then I went on to look at sort of a timestamp specific one, which is ignoring the time dependent element, called a random forest. Now, when you're looking at a classification model, there are three key metrics that really tell you sort of model performance. These are the precision, the recall, and the error, or the F1 score, that I'm going to probably use interchangeably here. Now, the precision is for all the times your model is making a prediction, what proportion of those were actually correct, what were a true positive, and what proportion were a false positive. And your recall is for all of the known positive readings we're getting here, what proportion of them, for all the known positives, for all the known class groupings we have, what proportion of them is the model able to detect? Now, for this initial model that's trying to do everything all in one go, it really, really struggled to get both high recall and high precision at the same time. I could either get one or the other. The trouble with this was that when the data was structured like this, it's got something what we'd call a class imbalance. Because the vast majority of the data that the model was being trained on was sort of normal data, the model was getting really, really, really good at predicting normal data. And it would assume that the majority of data was normal because that was what would give it the highest accuracy. Now, there are ways that you can sort of handle this, assigning different weightings to the different classes and stuff like that. But none of them were kind of working for this. The imbalance was far, far too great. So this led me to the conclusion that, this sort of model where it's all in one would not be appropriate. Instead, we came up with this idea of actually we should be looking at a chain of individual models, all set for a specific task. So the first one that we wanted to, the first stage that we want to do is we want to be able to sort of detect anomalous data and just label it as anomalous. The first model wouldn't really care about classifying it. It would just sort of flag this new data point, this new timestamp has come in. Is it normal data or is it abnormal data? This could then get fed into a sort of classification model that's just classifying between different types of abnormal data. And then that would trigger the appropriate, do we track and trace? Do we reconstruct data? Is this just sort of like a bunch of leaves have fallen into the river on one day because it's autumn or something like that? Now, this would require, this sort of framework is done a lot in engineering in sort of different fields, but it would require data engineers to be able to handle the structure of incoming data and just to make sure that all of this could be implemented. And you'd need models trained for each catchment. So what I've done now is I've gone through the different potential models we could have at each stage to just check their performance and how they could look and how well they work. So the first stage is this one. Can we distinguish between normal data and anomalous data easily, robustly, and efficiently? So first, I looked at something called principal component so principal component anomaly detection. So this is an example of what this sort of looks like. The idea is that you take all of your variables you're recording at a sample, at a site, over the entire period of time you've been looking at data there. You describe all of that using what's called a principal component model. Now, these are models that basically just sort of explain the natural variation you see in your data based on the variables you have. They're all about reducing dimensionality and complexity. So it'll just fit a sort of the first principal component through the data and rotate that to become the x-axis. And the values on the first principal component is actually just sort of a composite of the values along that of the variables along that line. Say, for example, an increase of 1 on the first principal component in this axis might signify an increase in conductivity by 7, a decrease in temperature by 3, and so on. Then it'll fit another principal component along the line that explains the second most variation and rotate that to be the y-axis. And again, it'll just be a sort of composite of the other variables you've monitored there. And it'll keep doing that until it's got one axis for the number of variables you have in. The first and second principal component will always explain the most variation, and each individual axis will explain a bit less variation. So the idea with principal component anomaly detection is you recreate your data by excluding a couple of the smaller principal components. The idea is that anomalous, strange data should mostly be explained by the later principal components, and the baseline should be captured by the former ones. So then when you reconstruct it, excluding the later principal components, you'll start to see a bit of error, a bit of deviance between your actual observed values and your reconstructed. You can then sort of train this threshold over which you sort of say everything above this threshold is anomalous data. And you can train that based off like historically labeled and identified data. So this is actually an example from the Eden DTC. All of these data points in red here have been labeled and identified as sort of normal baseline data, and these blue points have been labeled as sort of anomalous. This was actually driven by a broken phosphate probe on one of the Eden DTC sensors, which was quite interesting. So this technique is really, really efficient to use and is quite simple. The only the nuance with it is that ideally you need to have some sort of labeled data so that you can calculate what that threshold to define an anomaly should be. Now, the limitation with that principal component-based technique is that it is using data from an individual sensor. So say, for example, that sensor was somewhere really, really dynamic, where it's just experiencing a lot of natural flux. There's a lot of potentially there's a lot of pollution coming through the river. It's maybe below a sewage point, so it's getting a diurnal spike in conductivity or something like that. Models there would struggle a lot more with being able to define normal versus abnormal data. So another approach would be to use these models that actually use the values from sensors all around from neighboring sensors. So a prime candidate for that is something called a graph neural net. These are a very, very new addition to the sort of neural net framework. And they're basically capable of handling these non-linear structures. They use the spatial connectivity between sensors as part of their predictive capability. So this result is actually one we got from an Alan Turing data study group that we ran last week, where we asked a bunch of candidates to sort of explore how well graph neural nets work in catchments, how sort of sensor position impacts them, and how few sensors we might need to be able to fit them. And what we found is that graph neural nets perform exceptionally well in freshwater catchments, so well that it's actually difficult to say what affects their performance. They just work really, really well. We did find a slight thing, like, some upstream sensors seem to be a little bit harder to predict, but I think this methodology needs to be expanded and moved to different catchments. Now, the idea for using a graph neural net as the baseline model is basically you would build a graph neural net that would predict the values at, for example, sensor C, based on all the other sensors in the catchment. And you would train that off known baseline data. Now, because you've not told the model, you've not trained the model on sort of anomalous, abnormal data, you would ask it to predict a value for sensor C at every reading, and then you would measure the difference between that predicted value and the observed value. When you start to see a spike in that predictive error, we can infer that that will come from some sort of abnormal event. Just similarly to the principal component technique, you would specify a sort of threshold value that you would have trained off, the known rate of abnormal events for that catchment. This is just a technique that would be a bit more complicated to fit, but would be much more robust, and it would start using these sensor networks as actual, conglomerates working together. So that has looked at our anomalous data detection. So say, for example, we've done that. Now we flagged that we have this anomalous time point, this anomalous reading. The next thing we want to be able to do is say, okay, we have an anomalous data point, we have an anomalous timestamp. What is it? What type of event is it? Is it something we should be concerned about? Is it okay? And then to trigger the next stage of the chain. Now, the key questions we have for here is, for the type of events we're seeing, how many variables, more or less, can we get away with? Can lower cost sensors only measuring 3 or 4 provide as much information as higher cost sensors? And what variables, what combinations of variables are being the most impactful? So overall, this is a classification-based technique. So I used random forests as we used in the previous stage. And what we found was that when you don't have this major class imbalance, actually these random forests are able to perform that task really, really well. So this is the recall and the precision of every different combination of variables in the catchment, Wensum catchment F. So what I did is I fit a random forest for each site in the Wensum DTC, distinguishing between the different types of anomalous event we detected there. And then I ran every different combination of the variables I looked at for each individual site. So it ended up being 31 different random forests for each individual site in the Wensum DTC, coming to about 1,500, 150-ish models. From each model, I took out the precision and the recall, so the rate of true positives, and being able to detect all of the appropriate models. What we found is that models that had 4 or 5 of the vast majority of all the variables we had at the site, they got really, really high levels of precision and recall. They were more than probably about 95% of the time, they were identifying true positives, and they were able to detect all of the known events that we had. Now, what we found is that when you started getting down to looking at models with only 1 or 2 variables, there was a lot more variation in the overall performance, depending on which variables were included. But interestingly, models that had 3 variables could have just as high performance as models that had 4 in, which was quite an interesting finding. Now, what we wanted to do next was we wanted to try and work out what variables in the Wensum DTC were actually driving this overall relationship. So we looked at fitting variable importance plots against this and drawing out the average overall trend. The labels have gone missing here for some reason, but this first graph here is a model explaining overall error based on which of these variables was included, precision and recall. Consistently, we found that it was turbidity, stage, and conductivity that were providing the most information in the Wensum DTC subcatchment. We also looked at the interactions between these variables on their impact on importance. And, again, we found it was this interaction between turbidity, conductivity, and stage that was providing the most information. So these interactions are basically sort of synergistic, non-linear effects that including each of these variables had on each other. So a model that had turbidity, stage, and conductivity in together would actually perform better than the sort of individual sum of each variable alone. Sorry, that's a bit of a long-winded way to say that. Basically, they interacted quite well with each other, and including them together made the model much, much stronger, which was an interesting result. Now, there is a little bit of nuance here. The Wensum DTC, the Blackwater drain subcatchment, it's quite small streams there. It's probably one type of land use. There is no sewage or CSO points. There's no urbanization at all, really. So it's likely that, these results will vary depending on what catchment you're in and what sort of stresses you would expect to see. But what it does show is that machine learning models are able to perform really, really well with less information. I'd probably recommend that for the Casco catchments, you maybe just sit down and speak with local water quality experts, have a look at the maps of the region, what sort of stresses you might want to be able to distinguish between, what information you're looking to collect. But these models are ready to be deployed in these catchments, and they are proving quite effective so far. So, now we can say we have a technique either using graph neural nets or PCA that can really easily distinguish between anomalous data and normal data. We have techniques that can really easily classify the different types of anomalous data. So the final bit I looked at for the internship was, okay, if we detect a malfunctioning sensor, can we reconstruct the information there till it's repaired? So in this idea, basically, we flagged that we've got a broken sensor. The phosphate probe is just going a little bit. It's drifted off and it's giving out really weird readings. We sent out an alert to local citizen scientists or to the local management team, but it might be a week or two because the weather's terrible, or there's just a long list of stuff that needs to be done until that sensor can get looked at. Can we reconstruct the data at that sensor until it is able to be repaired? So again, there are two kind of ways that we can look at this problem. This is in essence is another supervised machine learning problem. It's a regression. Now we can either look at reconstructing the data at that sensor, either from that sensor's unique history, unique data, or again, using a graph neural net, using information that we're drawing from the neighboring sensors around it. And again, the questions we really wanted to ask here were how many variables are sort of needed overall, and what variables are having the most overall impact. Oh, I forgot about the arrow. So this is our case study. This is a broken phosphate probe in the Eden DTC. I would have liked to have stuck with the Wensum DTC, but unfortunately the data was far too well cleaned and they removed all broken sensor data at that point. Now, the idea here is basically, first, again, we looked at using a random forest-based approach. We trained a model to predict the value of phosphate based on all of these known normal timestamps, and we predicted it from the other variables the sensor was recording at the time. Then the theory would be if you flag that the phosphate probe is broken, this model would kick in and start predicting what should be there at the phosphate probe, and you would just sort of take that as your reading instead. Now, this technique actually worked surprisingly well. So the graph on the left here is the actual total phosphorus values we recorded on a standardized scale. And the values on the right here is actually the reconstructed time series. So the red points are the anomalous data, and the black points are the known normal data. So we still get this thing where we're getting these spikes coming up. Because this data wasn't actually labeled, and I labeled it with the sort of high-level sweep using the principal component technique, I can't say for certain that all of these data points that the model was built from are actually sort of accurate. What we were finding was that the models were able to get up to sort of 95% accuracy in predicting phosphate from the other variables we had recorded at the same time. Again, we found this pattern where the models performed best if they had all of the other variables the sensor was recording at the same time, and that would start to drop off the fewer variables we fed the model. We started to see, even with 4 variables, the model was performing really, really well. With 3 variables, it still performed really well, but we were starting to see more of a downward tick depending on what was provided to the model. This sensor, it was a flow rate, conductivity, and pH that were providing the most information overall to the model. Eventually, the initial models included turbidity, but I later dropped that because the turbidity probe in the Eden DT, that sensor kept going offline, which limited the amount of data we could feed to these models. Overall, I actually filtered out some of the weaker interactions here. There were fewer interactions for predicting phosphate at this sensor. Largely, we know it was flow rate and conductivity that were most important, and they were also having this really strong interaction on each other, which would probably be to signify between sort of different types of rainfall event and times of the year. Similarly, there was a weak interaction with pH, but also there was a stronger interaction between flow rate and dissolved oxygen and conductivity. So either of these combinations probably would have done a pretty decent job in predicting the phosphate value at that sensor. Now, again, this model comes with a limitation that it's using an individual sensor's data to be able to reconstruct what's going on there. This becomes less viable if multiple probes at the same sensor have broken, or if there's other complicated stuff happening at that sensor. So again, we looked at this sort of graph neural net approach. How well can we use the neighboring information from sensors to be able to predict the values at a given sensor? So graph neural nets, they've not been deployed too much in the freshwater environment. I fully expect that they are going to be a game changer for our field. They basically could use the weird and complex structure of rivers as information. The problem with normal traditional spatial regressions and stuff like that is that you can do things like Euclidean distance, where you assign sort of a decaying weight, but actually that might not be relevant. You might get a system like this where you've got 2 sensors on neighboring tributaries that are physically quite close to each other, but actually, they're not really connected. So flow propagated variables wouldn't matter there, and they might not be that similar. So a graph neural net can use this actual, watercourse related connectivity and flow connected connectivity as information. So as part of the data study group, we wanted to look at how well do these models perform overall? How does the number of sensors in a catchment impact their performance? And how does the location impact their performance? So just repeating myself a little bit from earlier, but graph neural nets performed exceptionally well overall. So for the first stage of the data study group, we built a neural net that looked at targeting all the variables recorded at each of these sensors from all the variables recorded at every other sensor. Overall, the error was, about 1% for predicting all of the variables on average. We kind of expected that tributaries would be harder to predict than mainstream things, but really we didn't see too much of a problem. We didn't see too much variation. We also went on to look at, if we were just targeting the more difficult sensor, a tributary sensor. So in our example, we looked at sensor C. We then built basically every combination of sensors in GNN from all 5 sensors down to every sort of possible 2-way connection. And we sort of assessed model performance based on whether that sensor was included or excluded as a rough sort of proxy of where we could get the most information. What we found is that for predicting sensor C, it was actually sensors E and F that provided the most information to that sensor. Sensor D provided the least information overall, and A and B also didn't provide as much. Again, the difference in performance here is, less than a percentage. The models performed exceptionally well. We think that this might be to do with the scale and the stability of the Wensum catchment. We believe that this methodology needs to be applied on a much bigger sensor network as, a proper catchment scale with miles between sensors. But it was still quite an interesting finding to just demonstrate how powerful graph neural nets are in the freshwater environment. They're a really prime candidate for any of these sort of baseline abnormality flagging models you want, any data reconstruction. Graph neural nets are able to handle it really, really well. Now, the overall conclusions are basically the models, the techniques that we've been looking at have been incredibly effective for the tasks we've been using them for. So it is quite feasible that quite smart and reactive sensor networks can be used and deployed on low-cost sensors that will be able to provide more information than just getting a CSV full of the rows of readings. We can quite easily automate sort of pollution detection, abnormal data detection, and the appropriate responses. Certainly for the Wensum DTC, we were getting really, really high performance of just 3 different variables of just conductivity, stage height, and sort of DO, turbidity rather. And they're 3 quite easy, cheap, and cost-effective ones to be looking at. In some circumstances, we were able to distinguish between 9 different types of abnormal event from just a combination of these 3 variables. Now, this will probably be catchment and site specific. The importance of different variables will change based on what sensors you're looking at, but it demonstrates that sometimes we can get away with a lot less than we might think we need. Particularly, I think graph neural nets are going to be a really, really powerful and effective approach for this sort of methodology. Unfortunately, not a lot of the sensor networks already exist that allow us to really test and train these methods. But I think as Casca starts to get going, we can start looking at these more sophisticated machine learning techniques. I think that's all I had, but were there any questions? Did I have my microphone turned on?
Yes, you did. Thank you very much, Andrew. Yeah, any questions? Either pop them in the chat or put the hand up, perhaps.
Sorry, Arena, you have a question?
Yeah, thanks. Really, really, really inspiring talk. Really enjoyed that. I was attending a talk by Kerry Mengersen, her research lab at Queensland Uni. They use Bayesian spatiotemporal models to do the similar thing that you do with the graph neural networks here. And she highlighted that one of the challenges with the SON data is that when we talk about abnormal data, an event a real event in the environment can produce a very similar data pattern to a broken sensor. And I was wondering how you dealt with that. Was that just not an issue for you because you had pre-labeled data and somebody had already made a sort of guesswork distinction between the two?
So from my understanding, it depends on, so we've worked a lot with Matt Lowenthal, who was the Environment Agency's head sensor guru, but is now a sort of private contractor. And his advice was that for things like a turbidity probe or phosphate, if it's a catastrophic sensor malfunction where the sensors become sort of buried or exposed to wear, you'll just see a sort of complete and catastrophic drop in the value. But it's the sort of the ion-based ones that are a little bit more susceptible to that sort of variation, where you get these sort of more gradual drifts that are quite difficult to distinguish from normal data or from things actually happening. The advantage for me was that the Wensum DTC, all of that had already been removed. They've had someone looking at the data every 2 weeks for the past 10 years, so I didn't have to worry too much about it, and all the catastrophic failures had been removed. The only time where I was really looking at broken sensors directly was in the Eden DTC data reconstruction project, and I specifically I did a high-level sweep to remove all the catastrophic failure myself, and then I sort of just targeted the probes that I knew would be subject to this sort of sensor drift, so the phosphate probe. It is one of my recommendations, I think, is that these machine learning techniques can be deployed quite easily, but we data scientists are not water quality experts. So there needs to be an element that some of the data needs to come in and be labeled, and you kind of need to be able to capture that level of variation. So you'd need a water quality expert to come in and be like, look, this is phosphate drift, where this is a pollution event, and then we can train the models to look at that.
Yeah, and I guess the challenge is for somebody starting out new with the new SONS work, they don't have 10 years of labeled data. So, and that I think that was kind of what Carrie's group is trying to look at. How would you make those distinctions on unlabeled data based on really fine pattern differences, I suppose, in those two kinds of events? Yeah.
From what I can tell, I think so. There's a technique called sort of semi-supervised learning where you only need to get a sort of subset of the data to be labeled. So as a rough rule of thumb in my mind, if you could just say, for example, 10%-ish of the data maybe gets labeled by citizen scientists, and then 10% of that might get just double checked by water quality expert. Even if you don't know all the types of anomaly that are coming in, if you can just get the sort of the rate at which you're seeing anomalous data, and then you could use some of like the PCA-based techniques of the GNNs to sort of flag that, to calculate that threshold, that should hopefully be able to detect it. But there will need to be this continuous process of experts and scientists checking the models to make sure they're performing. And then the more data you've got coming in, the more refined those threshold calculations become.
Thank you.
Yeah, I would just say on top of that, having worked with water quality sensors myself, probably the best place to do that labeling is kind of as close as possible to the people deploying and the time that the sensors data is being collected. So, good record keeping that can transfer into kind of high quality labeling of these data sets will be really useful in getting them kind of machine learning ready, I think. Okay. Questions in the
Bill
chat?
has asked if we've looked at any other water quality data from normal water quality sampling. No, I primarily looked at the water quality sensor data, just because we did consider using sort of point sample water quality data as a way to sort of validate some of the models. But when we thought we might have less data, with the WEN from DTC, I just had so much water quality sensor data that adding in other types of data collection with different biases and so on would probably have just muddied the water a little bit. I specifically wanted to look at these machine learning, the sensor techniques. Mandy Robinson has said, are there any plans to use this approach on sensors up and downstream of CSOs?
Bill's popped his hand up. Andrew, so
I'll just
thank you, Andrew. Yeah, I just wondered. I'd assumed that was the reason why you'd probably done that, because there was just so much data. I just think with your predictions, there was an awful lot of work done for the Water Framework Directive on predictor variables for all sorts of chemical and biological ecological responses. And yeah, as you said, conductivity, flow are key, but alkalinity is one which sensors don't measure. So you have to do it in the lab, and that was found together with altitude to be some of the strongest predictor variables you could use for a whole range of things, including ecology and nutrient chemistry, especially phosphorus and nitrate. So yeah, it would just be interesting to see if we could, build on what you've done and add something into it, because I think that would really improve the power of the modeling. It would be fabulous. Really interesting talk. Thanks.
So for Mandy's question, I don't know directly, but one thing that I think is an interesting idea is, those upstream sensors that are going to be deployed as part of the Environment Act are exclusively there to sort of calculate a baseline for the downstream sensor. And an interesting alternative that could be explored is this use of graph neural nets, where instead of just using, a sensor 200 meter upstream, you're able to predict what values you should expect at the downstream CSO sensor very easily. And if that could be sort of used if we have a much better understanding, and it would need to be tested a lot, but that's actually a way that you could sort of use the downstream CSO sensors from other regions in the catchment to be able to just create this simulated baseline, effectively using half the number of sensors. That's where the initial idea for graph neural nets came from. I mean, I don't know much about that, and there's a lot of work that needs to be done on graph neural nets. But so far as I'm aware, Casco and the environment, the CSO sensors aren't doing much together, are they, Simon?
Not at the moment. So what I would say to that is there aren't any kind of firm plans at the moment to use either sensors or machine learning on those data sets, although that's not to say they won't emerge as things develop with the Environment Act monitoring. What I would say is that we're working with a load of different demo catchments throughout the Casco project, and some of them definitely have plans to deploy sensor networks. As you can appreciate, we've learned an awful lot in the last 7 months with Andrew on board, and we're in a much better place to take that forward. I think whatever the sensor network design and whatever the purpose it is designed for. So, I mean, if you are deploying or have deployed a sensor network, please talk to us, and we'll see how your data can be kind of manipulated or kind of augmented, or the more get out of it using these kind of techniques. I think there's a lot more potential power to what Andrew's shown we can do than just kind of using it to analyze upstream and downstream of a point source, that kind of thing. And that's a lot of what Matt Lowenthal's team did at the EA. What we're looking at here is kind of more the ability to characterize catchments in different types of catchments and different areas of those catchments under different types of pressures, of which the CSOs will be a part.
Victoria, yes, I have. Richard Cooper was kindly providing me access to the full Wentham DTC dataset. I'm going to be sending him sort of a copy of the report and the output and recordings. But beyond him providing the data, I think he was just happy to let me go ahead and get on with it.
Yeah, no, that's cool. Sorry, it's Bitty. They're obviously part of Casco as well. They're going to have PhD students looking at looking at things in this space. So there might be a really good opportunity to create some more data through that can be used through this. So just keep in touch with them, I guess, on that. So yeah, but well done. It was a really interesting project. So thanks for that work.
Were there any other questions, or Heather?
Hi, Andrew. So we've been using sensors in the even load catchment, and one thing that we've come up against actually is the EA and accepting of the data, of the sensor data. And I think you mentioned this in your talk about being able to show how reliable the sensors are through kind of showing where the data's showing abnormal issues. So I think perhaps that's an idea for Casco. Well, something really important for Casco to think about is when using these data types is, again, being able to show the reliability, I think, is really important. I don't know, I suppose that was both a point and a question to follow up is what would you recommend? You mentioned the PCA approach. Are there other ways?
It's difficult, really. So it comes back to this point that the data needs to be labeled by citizen scientists or experts a little bit at first. Principal component threshold detection or GNN threshold detection, both of which would be able, once you've got a rough idea of what sort of threshold error you should be looking for to label as anomalous data, should perform quite well over the time series. And obviously you'll need to keep retraining the models and relabeling the data as time goes on, because unfortunately climate change is real. We live in a changing environment. So, you would expect over time, if you're not updating them, the models will become less accurate and start throwing out more and more errors. So it's about trying to find that way that actually you can use citizen science in a way where you can label the subset and then use that to train, to sort of seed the model that'll label the rest of the data. But just from that, you'll have, if that model is working well, you'll just have what proportion of your data is coming in as sort of anomalous. And it should also be able to classify the different types of anomaly that you're seeing, which will be interesting information, because that should also flag out things like, I know there's a lot of difference in performance between different types of probe, and some like ion probes might be more susceptible to an error than an optical probe, and it would be able to just sort of help feed through that.
I think also it's worth bearing in mind, we gave Andrew quite a few things to look at from a standing start as well. I mean, because we at the Rivers Trust were really keen to kind of get our foot in the door, I suppose, with machine learning. So we kind of knew which questions were worth pursuing. And Andrew's been really useful for that, for sure. That whole sort of sensor performance and kind of quality assurance of sensor data is definitely an avenue that could be pursued. And I know there are sensor manufacturers who are doing that. You know, if you are a manufacturer of a turbidity probe, then you know very well how it will degrade, and a lot of sensors actually have sort of diagnostic data built in, so there are parameters behind the scenes that we're not particularly interested in from a water quality point of view, but they do inform how the sensors are working. So again, we've really just scratched the surface, but by accessing some of those diagnostic data streams and working with manufacturers directly, we can see that, you know, it could be incredibly powerful for helping to quality assure data and predict sensor failure even.
Were there any more questions, or?
So Bill's posted about a new EA hydrology data explorer, so that sounds interesting, and it includes their continuous monitoring sondes apparently. I would say we had fantastic support from Matt's team at the EA, but it was interesting to note that a lot of their sensors are deployed for relatively short periods of time, and typically upstream and downstream of known or suspected problem sources. So not especially well tailored, I guess, to the kind of catchment characterization baseline we're starting from. That's Nicholas's. Yes. Yeah, and that's interesting as well. You know, again, speaking with Matt, he was kind of confident that sensor failure or sensor issues wasn't really much of an issue, and I think that's testament to the experience he has with deploying sondes. I've seen lots of sondes deployed in ways that do kind of generate dodgy data, shall we say. Okay, brilliant. Well, if that's everything in terms of questions, if not, get your hand up now or forever hold your peace. Thank you very much, Andrew, for that presentation. That was brilliant, and also obviously for all your work over the last 7 months. It's been fantastic, and we hope very much to tempt you back when you've finished your PhD.
Yeah,
but
thank you very much, everyone. It's been a great experience, this internship, and if anyone's inclined to try an Alan Turing internship, I'll recommend it. But yeah, I've got 3 months now until the end of the PhD, which should be a fun, stressful little break to get back to.
Yes, absolutely. Okay, brilliant. Well, thank you very much, everyone, for coming, and thanks again, Andrew. And I'll check out now, I think.
Thank you, everyone. Bye.
Cheers. Bye-bye.